Hello and welcome. This is recording attempt number 7. It's not going to take the full 10 minutes. This time I think I can do it in 4 minutes. So let's go. We'll talk about deep graph matching via Blackbox differentiation of combinatorial solvers. The task at hand is key point matching. A pair of images comes on input together with key point locations. The expected output is the matching of the corresponding key points. Feel free to pause the video and enjoy the difficulty of these examples. We have seen that the examples include non-rigid objects and changes in scale and orientation. Therefore, any method that wants to be successful needs to combine strong feature extraction with good combinatorial reasoning. Additionally, since there is only a small number of images available, there needs to be good combinatorial generalization. These are the reasons why this benchmark became a playground for aspiring deep graph matching methods. This line of work has produced some very well-received papers, most of which have focused on learning the combinatorial component. Our standpoint is different. We don't want to learn how to solve combinatorial problems, because there are expert combinatorial algorithms that are really good at it. What we want to do is take these algorithms and embed them into end-to-end trainable neural network architectures. This is possible due to a recent work of Vlastelica, also from our lab, which enables precisely that. Take Blackbox implementations of combinatorial solvers and freely embed them into end-to-end trainable neural networks. On a technical level, it is based on replacing the piecewise constant loss landscape by its efficiently computed piecewise linear interpolation. Another important element is processing of the geometric information. It turns out a lot can be extracted from the pure locations of the key points if they are processed properly. And the architecture that processes them best seems to be spline convolutional neural network, a graph neural network architecture proposed in the context of 3D meshes. All in all, our building blocks are the following. For local features, we use the VGG as it is standard. For geometric features, we use the spline convolutions as was proposed in some earlier work. For the matching procedure, we use the state-of-the-art solver, that is our novelty. And additionally, we introduce global features, which we also take from the VGG. The resulting architecture then combines all the visual, geometric, and global features into a graph matching instance. This instance is fed to this efficient solver, and the solution is compared to the ground truth, a loss is computed, and the whole architecture is trained end-to-end. The key point being the presence of the solver. If we look at results, qualitatively, we can see major improvements in handling changes of orientation. And quantitatively, on the most prominent benchmark, Pascal block, our architecture is ahead of the competition by a large margin. Additionally, we introduce multiple novel, interesting experimental setups. There are other advantages of having solvers inside architectures than just performance. For one, it simplifies the whole architecture design, since we can focus on constructing good features and good instances instead of constructing matching procedures. And we can handle more interesting combinatorial setups, such as having outliers, unmatched key points in one or in both images. And finally, we can use stronger, slower, but stronger multi-matching solvers for post-processing. If you are interested in code, please check it out. There is code for Blackbox differentiation, Blackbox deep graph matching, and for the combinatorial solvers. Thank you.